You've probably heard of the term entropy before. It's often described as chaos, disorder, or randomness. You may have heard that the entropy of the universe is constantly increasing even at this very moment. But what does all of this mean? Stay tuned for this video and you'll find out. Entropy is a measure of how spread out energy is in a system. Low entropy refers to a state where all the energy of a system is concentrated in a single location. On the other hand, high entropy refers to a state where the energy is spread out evenly throughout the entire system. This all seems very abstract, so let's look at a simulation to understand the concept intuitively. In the previous video on energy, I showed a simulation that demonstrates how energy moves through a row of marbles that are connected horizontally by springs. Let's take another look at that simulation. Initially, only the two marbles on the left have energy. Is this low entropy or high entropy? It's a low entropy state because all the energy of the system is concentrated in two marbles. In fact, we only see movement in these two marbles at the start. As the simulation evolves, what do we see? More and more marbles start moving, which means that the energy has spread to more of the marbles. Remember that entropy is a measure of how spread out energy is in a system. This means the entropy in this simulation is increasing with time. Notice something else? At the start of the simulation, we could see a point of maximum energy that was moving through the marbles to the right. After reaching the right boundary, that point then started moving to the left. However, after a while, we no longer see any point of maximum energy. All the marbles appear to be moving randomly with the same amount of energy. This is what a high entropy state looks like. Now you can see why entropy is often associated with chaos and disorder. The simulation has become drastically more chaotic now when it is in a high entropy state than it was at the start when it was in a state of low entropy. But why does entropy increase? If you look closely, whenever a marble moves, it creates an imbalance in both the marble on its left and the marble on its right. That is, it transfers energy to both its neighbors. Now that the neighboring marbles have energy, they too will move, thus creating an imbalance in their neighbors as well. Some of the energy has returned back to the first marble that moved, but some energy has also spread out to two new marbles. This process repeats itself continuously, with the energy spreading out to more and more marbles over time. Now that we know what entropy is and why it increases with time, the question that remains is, how is this relevant to the real world? In fact, if we examine a real-world system, we see that it behaves a bit differently from the simulation. Take this drawstring, for example. At first, it behaves just like the marbles in the simulation. The energy travels down the string until it reaches the end, after which it moves back towards my hand. Also, just like the simulation, the energy spreads out across the entire string. However, notice that the string eventually stops moving, whereas the marbles in the simulation keep moving indefinitely. What's happening in the string? Well, actually, the same thing that is happening in the simulation. The energy is spreading across more and more marbles, where the marbles in this case are the atoms and molecules that make up the string. The organized movement of the string turns into disorganized molecular motion that we cannot see with our eyes. However, this molecular motion can be measured as an increase in thermal energy or heat. This energy is eventually dissipated to the environment in which the string is contained. We can observe the same behavior in the simulation when we increase the number of marbles significantly. The horizontal movement of the marbles is now shown as vertical movement, so we can see it more clearly. Notice that, as the energy spreads out, the movement of the marbles becomes less noticeable. The simulation also differs from the real world in that it is a closed system. This means there is nothing outside the marbles which can move or experience change. That is, there is no environment into which the energy of the marbles can be dissipated. As a result, the marbles retain all the energy that they were given at the start of the simulation. What the real world and the simulation have in common is that energy doesn't disappear or get used up, it simply spreads out, or in other words, the entropy increases over time. In this video, you learned that entropy is a measure of how spread out energy is in a system. Low entropy indicates that the energy is concentrated in a single location, while high entropy indicates that it is spread out evenly throughout the entire system. You also learned that entropy always increases with time in any system where energy can move freely. This includes both simulations and real-world systems. Thank you for watching, and I hope this video has given you an intuitive understanding of entropy. If you're confused about what energy actually is, please check out my previous video that explains what energy is at a fundamental level. The link is in the description.